From where I left off yesterday. This second hour will be on, I'll talk about the virtual fibering problem, and then the third hour I'll talk about some aspects of the proof of this theorem here that I mentioned last time. So this was a conjecture of Wise. So I'm not sure how much people know about this Wise's work. I guess in 2009, I think he had a research announcement that he had proved a fairly general theorem about Lerf subgroup separability and residual fineness properties, linearity properties for hyperbolic groups that have a quasi-convex hierarchy. Now, just for the sake of simplicity, I didn't want to get into all the general aspect of Wise's theorem during these talks, but I wanted to indicate that I'm actually making strong use of the progress that he's made over the past decade or so. And in some sense, Wise has been working on this ever since he was a graduate student to solve a problem originally due to Baumschlag about whether if you have a one-relator group with torsion, so you have a group with a presentation that has a single relator that's some proper power, then he proves that those groups are residually finite. And this is a problem that he had worked on for a long time. And he resolved it in this preprint, which is 180 pages or so. It's it's a little bit in flux. It's changed several times. But anyways, it's a very long paper. It's also based on previous results, joint work of him with Tim Hsu and Frederick Haglund. So all in all, and so I'm making use of, I'll mention in the second talk what result I'm using, but the proof of this theorem makes heavy use of Wise's work. And I'll mention in a second some other of the consequences of Wise's results. But anyway, so if you have a hyperbolic group, like the fundamental group of a hyperbolic three-manifold, which is cubulated, so that it acts properly co-compactly on a cat-0 cube complex, which, as I mentioned last time, holds true for hyperbolic three-manifold groups by this result of Bergeron and Wise, then it's virtually special. So it has a finite index subgroup that injects into a right-angled Artin group in particular. And so, so all these consequences follow for the hyperbolic three-manifold. The fundamental group's Lerf. It's large. There's a finite index subgroup that surjects a free group, and it virtually fibers. So the proof of this theorem uses Wise's results. In particular, it's based on really sort of hundreds of pages of Wise's work. And I'm not going to talk about this result, the weak separability result, which is also key, but I'll indicate how that comes into the proof. But the first talk now, I want to talk about this older result that says if you have a three-manifold that's virtually special cubulated, then it's virtually fibered. So recall that virtually special cubulated means that M is homotopy equivalent to a cat-0 cube complex, which has a finite sheeted cover that has one of these special structures that Sam has talked about in his talk. And in particular, so there's a compact cat-0 cube complex homotopy equivalent to M, and there's a finite sheeted cover x tilde of that, which is special, so it has embedded hyperplanes, and it injects into a right-angled Artin group. In particular, the cube complex has a locally isometric immersion into the Salvetti complex for the right-angled Artin group. So, so I'm indicating here RAAG is a right-angled Artin group. It's an abbreviation that I think Sam talked about in his talk. So now, for these right-angled Artin groups, there is a strong form of residual solubility for right-angled Artin groups, which I call the Riefers property, which I'll explain in just a bit. And it passes to subgroups of a group. So if you have a group that has this Riefers property, residually finite rational soluble, then it passes to any subgroup. And what I proved in 2007 is or 2008 is that it implies then if you have a three-manifold with this fundamental group of this property, then it's virtually fibered. So that's the theorem that I wanted to explain today. And then, as I mentioned before, with Konda-Markovic's and Bergeron-Wise's theorem, we know three manifolds are cubulated, hyperbolic three manifolds are cubulated. So one thing to show then is that if the fundamental group is Lerf, then that will imply that M is virtually fibered. And so that's the theorem that I mentioned on the previous page. So one aspect of what Wise proved, so the preprint appeared, well, last year. There's preliminary versions that were distributed early. So anyways, I'm saying it's 2011, although I should say also that the results I'm making use of are actually, he published a strengthened version, or distributed a strengthened version in 2012 that I'm actually making use of. But this older result implies that if you have a Haken hyperbolic three manifold with a quasi-Fuchsian embedded surface in it, so it's something that's not already fibered, in other words. Remember, there's this dichotomy for surface groups. They either correspond to fibers of a fibration or they're quasi-Fuchsian. So if you start with a Haken manifold that's not fibered, then Wise proved that there's it's virtually special cubulated, and therefore from this other result, that's has a finite index cover that has Riefer's fundamental group and therefore is virtually fibered. And I should say that in the proof of this theorem, Wise gives a different approach to finding cubulations, which is based on his joint work with Tim Hsu, than the result of Bergeron and Wise. And it, also, his theorem holds a much greater generality than what I've stated here. It holds for hyperbolic groups that has a quasi-convex hierarchy. But I didn't really want to get into the technicalities of that. Suffice it to say that these Haken hyperbolic three manifolds with a quasi-Fuchsian surface, they have one of these quasi-convex hierarchies. It's a classical notion due to Haken and Waldhausen that allows you to inductively construct a fundamental group of a Haken three manifold by iterated amalgamated products or H&N extensions. And it's this inductive structure that makes the Haken manifolds much easier to analyze in a lot of respects, and Waldhausen was able to analyze them. And also Thurston, in the proof of his geometrization theorem, proved it inductively on a hierarchy. So it's a notion that originated in three manifold topology, or also in the concept of one relator groups, these hierarchies, and they make the notion of a Haken manifold very useful. So now I want to explain then this virtual fibering result. So to do this, I need to explain what this Riefer's term means. So it's a little bit involved, but I'll explain a geometric version. So this is the algebraic version. So the rational derived series of a group is defined inductively as follows. So I'll take G upper 1 to denote the commutator subgroup of G. And the rational commutator subgroup is you take all elements that have some power that's contained in the commutator subgroup. So that's one way to define the rational derived subgroup. And then you iterate that to get the nth rational derived subgroup. So the n plus first rational derived subgroup is the rational commutator, rational derived subgroup of the nth rational derived subgroup. So you define that iteratively. So it's just like the derived series, except you allow, you're getting rid of torsion. So it's called rational because it's really, another way of saying it is that the rational derived subgroup of G is the kernel. So I map G to H1 of G with Q coefficients, or to, I take G mod, its rational, its derived subgroup, and I tensor that with Q, so that just kills all the torsion. So when you take these powers here, you're essentially killing the torsion in the quotient. And so this quotient is a, if I take G mod G1 rational, then it's a torsion-free abelian group. It's just Z to the N or whatever. So you're just getting rid of torsion. That's why it's rational. And so these quotients are solvable because the rational derived subgroups are contained in the, so these quotients, these are containing the derived series, and therefore anything that contains a derived subgroup is going to be the quotient is going to be solvable. So then I say that a group is residually finite rational solvable, or REFRs for short, if there's a sequence of subgroups, finite index subgroups G0, G1, G2, which are cofinal, so that just means that their intersection is trivial, and such, so they're finite index, and each one contains the rational derived subgroup of the previous one. So G1 will have to contain the rational derived subgroup of G, G2 will have to contain the rational derived subgroup of G1, and therefore G2 will contain the second rational derived subgroup of G0, etc. So the Gn will contain the nth rational derived subgroup of G. Okay, so that's the definition of a REFRs group. So it's a very strong form of residual solvability, but because it's associated with the rational series, we call it residually finite rational solvable. So residually finite solvable would mean you could separate any element in the group inside of a finite rational quotient group. Here we're separating any element of the group in a finite rational quotient, but it's coming from this rational derived series, which is why it's much stronger. And in particular, you have to if a group's going to be REFRs, it has to start out having positive first Bay number. So even to get started, you need a group that's first Bay number is positive. So G mod Gi will be solvable. Here, I didn't say that these groups are normal subgroups, but you can just pass to the cores, and those will be normal subgroups. So we can assume they're normal. And so if I have a REFRs group, then any subgroup of it will also be REFRs, because you just intersect it with a rational derived series, and that will give a corresponding filtration of H, which contains the rational derived series. So it's it passes to subgroups. So examples of REFRs groups are free groups, surface groups, and right-angle Artin groups, which is why they're important in this theory. So that's a sort of abstract algebraic description. Here's a more geometric description. So for a three-manifold with REFRs fundamental group, one way of saying it, it's more geometric, is that there's a cofinite tower of finite index covers. So we start out with M, and we take a sequence of finite covers, M1, M2, etc., such that Mi plus 1 is obtained from Mi by taking a finite sheeted cover cyclic cover, which is dual to an embedded non-separating surface in Mi. Maybe I should try to draw a picture here. So we can think of Mi as it has positive first Bay numbers, so there's some surface sitting inside of it. So here's Mi, which is non-separating, and then Mi plus 1 is obtained by cutting. So you can think of cutting Mi along this surface, taking n copies of it and stacking them together, re-gluing them. So Mi plus 1 will look something like this. So you have a surface. So here's some copy of this guy, and then you iterate it n times. So for each Mi, Mi plus 1 is obtained from the previous one by some such construction, just by taking a cyclic cover. But it's a cyclic cover dual to a non-separating surface, which is homologically non-trivial. So it's not just coming from the torsion, which is why it's the rational, corresponding to the rational derived series. So that's geometrically. So then inside of Mi plus 1, we're going to find some other surface, and we can wrap along that, and you just iterate that process. And saying it's cofinal means that, say, the inject-Kidder radius of these covers goes to infinity at a fixed base point. So something like that. Okay, so that's the REFRs condition. Another way of saying it is that pi 1 of Mi plus 1 is a cyclic cover, but it's factoring through a homomorphism. So we have a homomorphism pi 1 of Mi to Z that then maps to a finite cyclic quotient. So it's factoring through the non-torsion part of H1. And also, this condition implies that M has virtually infinite first Bailey number unless pi 1m is virtually abelian. So, the right-angled Artin groups, like z to the n is a right-angled Artin group, that's a Riefers group. Whenever you take finite index subgroups, the rank always stays the same. But otherwise, the rank of B1 will increase to infinity in this when you have this Riefers condition, it turns out. So that's one property of these groups. So when you have a Riefers group, it starts out having positive first Bailey number, and by taking these cyclic covers, the Bailey number goes to infinity. So you're getting lots and lots more homology in these cyclic covering spaces, in these solvable covering spaces. Okay, so back to the theorem. If M is aspherical and pi 1m is Riefers, then M virtually fibers. So the proof makes use of sutured manifold theory, and so that's what I'm going to spend the rest of the talk talking about, is some of the ingredients that go into the proof of this theorem. And the notion of sutured manifold theory was introduced by David Gabai in the 80s as a technique for studying foliations of three manifolds. In particular, he used it to prove the property R conjecture. And it's similar to a hierarchy in that it's an inductive way of cutting up a manifold, but it's a little bit more carefully controlled than a hierarchy associated to a Haken manifold. I just wanted to mention this was one ingredient in a proof of Friedel and Vedusi, that if you have a three manifold, closed three manifold, such that when you multiply it with a circle, you get a four manifold which has a symplectic structure. So there's a closed symplectic form in there, closed non-degenerate two form. Then the three manifold has to fiber over the circle. So it was a theorem of Thurston and Winkelkemper, I think, in the 70s, that if a three manifold fibers over the circle, then when you cross it with a circle, there's a natural symplectic form of that manifold. And it was an open problem of, I think, Cronheimer and Taubes, that the converse was true. So they proved that, and one of the ingredients was this theorem, or actually a slight strengthening of that, we'll talk about. Okay, so that's one application of this condition. So it actually gives you a slightly stronger structure for the implication for the structure of the cohomology of M, H upper 1 of M. So for any cohomology class in H upper 1 of M, and here I'm taking a non-torsion class, but it's H upper 1 of M will be non-torsion if M's orientable, because it's Poincare dual H lower 2. Anyways, so then there's a finite sheeted cover where the preimage of alpha, so I'll call that, so you can just pull back cohomology class to the finite sheeted cover. It's a limit of cohomology classes which correspond to fiberings of M tilde. So if you have a three manifold with a non-trivial cohomology class, you can represent that by a closed surface. If this thing doesn't fiber, then this Riefers condition allows you to pass to a finite sheeted covering space where I can approximate this cohomology class by fibered cohomology classes. So in some sense, every cohomology class is at least up to finite sheeted cover, very closely approximated by a fibering. And that's actually the condition that Friedel and Vedusi are using. And actually, this also implies then that covering space, there's a depth 1 top foliation of M. So with a closed leaf corresponding to the Poincare dual of alpha tilde. So up here you would see a preimage of the surface, and there'd be some foliation which limits onto these closed surfaces. So after cutting along these surfaces, you get a fibration of the resulting manifold with non-compact leaves, though, that spiral onto these leaves. Anyways, that's just the top. That follows from Dave Gabai's sutured manifold theory that I was just alluding to. Okay, so now I think I'll go to the blackboard, and so I want to explain the proof of this theorem here and the sutured manifold theory. So So that's what I'll do for the rest of this talk. So I'll put this screen up, and then I guess I can just. Oh, so you can turn the screen up or mute that. Okay, thanks. So I want to talk a little bit about suture manifolds. But first, I need to say something about the Thurston norm on homology. So M is an irreducible manifold. Orientable manifold. And I'll assume that well, I'll assume chi of m equals 0. I actually will sorry, let me get rid of that assumption. So if sigma is an oriented surface, then chi minus of sigma is the sum over C over components of sigma of the max of minus chi of C, the Euler characteristic of C, and 0. So what you do is you take, so it's an orientable surface, but it might be disconnected. So you take all the sphere components, you throw it out, and you take the negative Euler characteristic of what's left. That's so that's chi minus of sigma. And then another way of saying this is, if you're familiar with chi minus of sigma, is 1/2 the Gromov norm of the fundamental class of sigma, and I'll do it with rel to boundary. So if you're familiar with so this is the Gromov norm of the fundamental class. If you're familiar with that, then that's fine. Otherwise, you can ignore this observation. So now if we have a homology class in H2 of M, rel boundary M, with Z coefficients, then we define the norm of Z to be the infimum of chi minus of sigma over all surfaces representing Z. And this is really the surface rel its boundary. So so there's some facts that Thurston proved about this. If I take n copies of the cohomology class, this is equal to n copies of Z. This is equal to n times the norm of Z. And oh, thanks. So the norm of Z extends to a semi-norm on H2 of M, boundary M, with R coefficients. So H2 of M with Z coefficients is a lattice inside of there, and it extends linearly. First you do it to extend it to rationals using this property, and then you extend it to the reals just using density. And this is, by point graduality, this is isomorphic to H upper 1 of M. So sometimes I'll talk about the Thurston norm defined in H upper 1, which is a little bit more convenient when you're pulling back cohomology classes to covers and stuff like that. Then, so if M is, or interior of M is hyperbolic, this is actual norm. So, in other words, non-zero homology classes have non-zero norm, and you can see why that's at least necessary. Maybe is that well here I should say hyperbolic with finite volume, I should say. So it looks like a manifold with torus boundary components. So if you have a homology class which is represented by a surface of zero norm, well, first of all, any sphere component will be homologically trivial because it's an irreducible manifold, so you could throw those away without affecting the homology class. So then you're left with a surface of chi minus equals 0, which means that the Euler characteristic of each component is 0, which means it's a torus or an annulus. But in a hyperbolic manifold, you can't have an essential annulus. And every torus has to be boundary parallel, so it would be 0 and H2 rel boundary. So anyway, so that's just a comment that it's actually a norm on a hyperbolic manifold. The unit ball is a finite-sided polyhedron. And if Z in H1 of M with Z coefficients is a fibered cohomology, so it's represented by a everywhere non-zero one form, then the face of the Thurston norm ball is fibered. Meaning that if I take any other primitive integral cohomology class and this face sitting inside the cone over the face of that Thurston norm of that containing that element, then any other element in there will also correspond to a fiber of fibration. So let me demonstrate on the Whitehead link. So here's the Whitehead link complement. So H upper 1 of M is two-dimensional. So this is S3 minus W. So here's W if you like. And there's some natural surfaces inside here. Maybe I'll draw it in a slightly different way where you can see the surfaces more easily. So I can draw the Whitehead link like this. And inside of here there's a disk with two punctures. The Euler characteristic of that is -1, so the norm of that surface is equal to 1. And so I get an element there that, and I can also tube together here, so you can sort of tube around. Let me draw it in a different color. So you could tube these guys together to get a punctured torus, which also has Euler characteristic -1 because you're just adding an annulus. So, and that element, that surface intersects a meridian here in a single point. So it's point gray dual to a meridian in H lower 1. Or sorry, H upper 1. I mean, anyways, the intersection number with this surface gives an element of H upper 1. So, so that's a point with norm equal to 1. But this is dual, so there's, if I take the weighted link and I exchange it to components, there's an isometry, so that there's also an element of norm 1 there. And it turns out when you take these surfaces, you can add them together in a way, and you get a surface that's Euler characteristic equal to, well, when you add them together, you sort of do a cut and paste operation. And you can just check, so I'm not going to do it here, but anyways, you can check that you get something of Euler characteristic -2. It'll have 2 boundary components. It's Euler characteristic -2, which means that it has to be a twice punctured torus. And so, so that's the element here. That has norm 2, so half of it will have norm 1. But this means that we've determined the entire unit ball, because we know that there's these points here on the unit ball. We know there's these points here on the unit ball. That's, again, something you have to check, but anyways, once you've, so the only way that that this could be a unit ball is if these faces are extended like that, and it's symmetric under rotation. So so that's a unit ball for the Whitehead link, and it also turns out that this surface is a fiber of a fibration, and so I mean, actually, this surface can be constructed just by Seifert's algorithm from the. You just choose an orientation on the 2 components and apply Seifert's algorithm there to get the surface. And you can check that that's fiber of a fibration in various ways. So, so this one surface is fibered, and that means that if I take any, so this is a fibered face, meaning if I take any primitive integral point inside of here, the cohomology class there will be dual to a fiber of a fibration. So that's what it means. So all these guys inside of here are fibered. But this guy is not a fiber of fibration. If I have a link complement which fibers are the circle, the fiber has to meet every boundary component. But this meets only one boundary component, so it's not a fiber of fibration. And that is corresponding to the vertices of this polyhedron, which are not fibered. So, so that's a brief introduction to the Thurston norm. So now I want to explain how this is used to analyze a how this Thurston norm behaves in these finite sheeted covers of a manifold with Riefer's fundamental group. Notice here that these elements of these non-fibered guys are in the boundary of the fibered face. So this already has this property that I was mentioning. So I need to say a few words about sutured manifolds. So as I mentioned, these are introduced by Gabai as a method of producing finite depth foliations on knot complements. So it's an inductive way of creating a foliation on a manifold. So now M is irreducible. We'll say the first Bay number of M is greater than 0, or M is a 3-ball for each component. So M might be disconnected. It's useful in the theory to allow disconnected manifolds. They'll crop up. In boundary M, we'll have a decomposition into what's called R plus and R minus and gamma. So gamma are called the sutures. is a union of a disjoint union of annuli and tori boundary components. So it consists of tori boundary components, and then in the other components, and maybe possibly some of the torus boundary components, you'll have some annuli. And these annuli will divide the boundary into R plus and R minus. So everything's oriented. So M is oriented. R plus and R minus are oriented. So that the normal vector in R plus, the co-orientation of will point outwards in R plus and inwards in R minus. So I'll draw a picture in just a sec. So in suture manifold theory, rather than drawing an annulus, we draw gamma as just circles. So, and then thicken that up to get the annulus, if you like. And everything has an orientation. So here's R plus, here's a 3-ball, and here's R minus. And these are oriented, so say R plus is oriented and outward. So you have like a right-hand rule, let's say. So there's an orientation that I'll draw by a little circle, oriented circle. And the right-hand rule then says that the normal vector will point upwards. In R minus, it'll point into into R. And so, and this is done in such a way that the orientations are both induce the same orientation on the core of gamma. So here I have this orientation on this little circle. See, it's consistent with this one, and this one is consistent with this one. It's like the winds on the surface of the Earth are sort of winding around. They meet at the equator in a consistent way. Okay, so so that's the most basic suture manifold. It's just the ball with this suture here dividing into two pieces. Another example is a surface crossed with 0, 1, or actually this is a special case of this one. Think of taking a surface like a punctured torus and cross it with an interval. Then here's gamma. It's this annulus here. Is boundary sigma crossed with 0, 1. And then R plus and R minus are sigma cross 0 to say R plus, and sigma cross 1 is R minus or something like that. So this is called a product suture manifold, and this this is a special case of that, actually. If you think of like a tuna can, a disk crossed with an interval is a special case here, and that's just a ball. So so this, say, will be pointed outwards up here, and so let's see how this. Oh, I wanted one more example of a solid torus where the sutures are. So maybe I should draw the sutures in some color like blue. The sutures here are just going to be. I choose any curve on the boundary, and I choose two copies of that curve so that it's separating. So R plus and R minus will be the complementary regions. I'm not going to draw the orientations here for simplicity. But so this would be a suture manifold as well. Okay, so those are some examples. So where do these suture manifolds come from? Well, if I have a manifold and I take a surface sitting inside of it and I cut the manifold along that, it's an oriented surface. So let's put an orientation on this guy. So say it's oriented like that. Then when you cut along it, so if I cut along that surface, I get a manifold with boundary, but I want to keep track of, well, I get a suture coming from the torus boundary components here. So there's these, when you remove the link, you actually remove a tubular neighborhood of it. So you're removing a sort of solid torus. So its boundary are two tori. And when you cut along the surface, then you're going to get a manifold, and I'm going to try to draw it now. That's a suture manifold in a natural way. So in this case, the picture is going to look like this. So I have this disk here, and there's some picture like this. I guess I won't draw the entire thing. So this is just repeating this picture, and there's so when we cut along this, what we get is a suture manifold that looks like this. Well, I'll draw this. Let's see. I was using blue for the sutures, right? So this guy will be blue, and I just get something that looks like this. And there's a guy down here as well. Oh, sorry, that should be red. Sorry about that. Inside of there's a blue guy corresponding to the other component. And so this is all red here. And this is R plus, and then inside of here you'll see R minus. And they're separated by this tube here that we cut along. There's a solid torus here coming from this boundary component. When we cut along it, we just get an annulus here. So that's intrinsic, and I sort of turn things inside out. It's the complement here. So this is sitting inside of S3, and it's the complement that we're looking at here. But now I've sort of redrawn it in a slightly different way, and hopefully I haven't confused everyone. But anyways, that's the suture manifold you get when you cut along this guy. So so I can sort of redraw this as just a torus, and then there's a solid torus inside of here, and then there's another suture here, and let's see. So now I've gotten myself confused. Let's see what what I'm doing here. Oh, right. Sorry, I was going to the next operation. I got a little ahead of myself here. Sorry about that. So now what we see here is a suture manifold, but there's a certain product structure here. There's these tubes go through, but there's sort of a partial product structure here. There's this planar surface crossed with an interval sitting here. So we extract that out, and I guess I'll use a different color, and we get this picture, which now has two new sutures. And sitting inside here is still this blue torus. So that's, and again we have R plus and R minus here. So this is just a torus crossed with an interval after cutting along this product piece. So this is a product piece. And now this is what I call the guts, or what this terminology goes to goodbye, of the sutured manifold. It's the maximal non-product part of the sutured manifold that we have here. So there's a large product part of it, and there's some essentiality condition here that this is an essential product part that I'm cutting along. So this is an essential pi1 injective. Each boundary component is not compressible. Product piece that's sitting inside of there. So you extract the maximal product part, and you're left with what's called the guts of the sutured manifold. Now, what does it mean to be fibered? Well, if you cut along a fiber surface, then when you cut along it, you just get a product sutured manifold. And so the guts is trivial. So I'm trying to get to explain where this Riefers condition comes in. And the point is that if sigma is contained in M is a fiber with a fibration, then the sutured manifold M, and I split M along sigma, so I'll write it like this. This is a sutured manifold. Is a product sutured manifold. If and only if sigma is a fiber. So I should put the if and only if here. And so otherwise, the guts of M minus sigma is non-trivial. So we remove. So there's a version of the JSJ decomposition here that it's underlying all this, which I'm not going to go into the whole theory of that, but just suffice it to say there's a canonical maximal product region that's canonical up to isotopy that's guaranteed by the Jacob, Schale, and Johansson, the JSJ theory. And what's left is the guts of the sutured manifold. So this guts is the obstruction to that homology class being a fiber of fibration. So the claim that's underlying this Riefers condition is that the rank of the image of H1 of M to H1 of the guts of sigma and here I need so here I should have said, sorry, let sigma be norm minimizing. So chi minus of sigma is equal to the norm of the homology class represented by sigma. And it's maximal. So I want to take a maximal collection of disjoint non-parallel surfaces homologically parallel to a fixed homology class. So I'll just call that maximal. And then I take the guts of that surface. And the claim is that the rank of the image is equal to the codimension of the face in the Thurston norm ball. So you can sort of detect the geometry of this point, like a point here, I'm claiming you can detect its geometry from, if it's a norm minimizing surface satisfying these maximality condition, then you can detect it from the Suture manifold decomposition of the complement, where it lies in sort of the Thurston norm ball. And so the point is here, well, let's look at it. Let's go back to this example here. Let's check to see how this works on this example. So we look at the guts of this red surface here, this torus, and punctured torus, and it's a torus crossed with an interval. So what's the maximum that H upper 1 of M image? So H upper 1 of M, it's the Whited link complement. That's just Z squared, right? We look at the A up. So this is so H upper 1 of S3 minus W is Z squared. That's Alexander duality. We look at the image in H upper 1 of the guts of sigma. Well, it's a torus cross an interval, so H upper 1 here is also Z squared. But the point is that the image, though, has rank 1, because if you think about it, this blue guy bounds, you know, there's two components here, a red and a blue, and this guy bounds it's bounding a surface, you know, you can sort of tube it together here, that's disjoint from the red guy, which means there's a curve, there's a longitude that's homologically trivial. And so the image of H1 has rank 1. Does that make sense? So in this particular example, the image of H upper 1 of M into H upper 1 of the guts is 1. And you see here it's also a codimension 1 face. It's a vertex of the codimension 0 would be something lying inside of here. Codimension 1 is a vertex in this case. So that's just exemplifying this claim here. In particular, if you take a cohomology class lying in a top dimensional face, then the rank of this image is 0 inside the rank of the guts. Now let's go back to this Riefers condition. So this is where the Riefers condition comes in. So if Z lies in a and also see that this works if it's a fibered guy, the guts is trivial. So the image of H upper 1 of M and H upper 1 of the guts of a fibered class is just 0 because it's H upper 1 of the empty manifold. So if Z lies in a maximal dimensional face, this rank is 0. So let's go back to the Riefers condition. Now, if our manifold, so we start out, so let's assume pi 1m is Riefers. So in particular, H1 of M with coefficients in R is not equal to 0. So either M fibers and we're done, or it doesn't fiber and we take a cohomology class, Z and H upper 1 of M, Z coefficients, lying in a maximal dimensional face. And now we take this sequence of covers. M is covered by a finite cover M1, finite cover M2, and so that pi 1 of M is the kernel of the homomorphism of pi 1 of M1 is in the kernel of the homomorphism of pi 1 of M to Z. Now, what does that tell us? So we pull back this cohomology class. So there'll be a Z here. There'll be a Z1 that's the pullback, of that guy, Z2, etc. And so we do this construction. We take a maximal collection of disjoint surfaces representing Z, which are not parallel. We take the guts of that, and the guts is non-trivial because it's not fibered. But the image of H upper 1 of M in the H upper 1 of the guts is trivial. So that means that this guts region, so the guts of Z, it lifts to this covering space, or each component lifts. It'll actually be, if this is a k-fold cover, you'll get k copies of the guts of Z inside of here. And so what happens is this guts is, it's going to lift, each component is going to lift to this covering space. There's something you have to check here, that if I take the guts of Z1, then this is so the guts of Z1 then will be a disjoint union of k copies of guts of Z. So that's what we get out of this this little claim here. We're just applying, actually we don't need the strength of this claim, just this fact that it's in a top dimensional face and the rank is 0. But that means that we can repeat this process. So we go to Z2 and the guts here will lift, except if the this guy might become homologically non-trivial. H upper 1 of M1 might map homologically non-trivially to H upper 1 of the guts of Z1. If that happens, then that says that our Z1 is no longer in a maximal dimensional face because of this criterion. And so the homology must have increased in dimension, H upper 1, and therefore you get a new homology class. And so you perturb your homology class into a larger dimensional face. What happens, there's a suture manifold decomposition. So if H upper 1 of Mi to H upper 1 of Z, guts of Zi, is not equal to 0, so the image of this, then that implies that that we can do we perturb Zi into a maximal dimensional face that's adjacent to it. And there's a little suture manifold analysis you have to do here. Then that implies the guts of Zi, which is just a union of the guts of Z, is a suture manifold decomposition. It simplifies. And there's a certain inductive argument then that you can only simplify by suture manifold decomposition these guts regions only finitely many times. So there's a complexity that Gobai defines. So if you have suture manifold decomposition, it can look something like you cut, for example, this guy along a disk, and there's a certain way when you cut along it to get a suture manifold where you do an oriented sum of the curves in the boundary, and you're going to get it turns out you get a taut sutured ball. So it's something you have to check here. These guys are going to be oriented in opposite ways. And you get this, in this suture manifold, when you cut along, when you do this decomposition, it simplifies. There's a complexity that decreases. There's actually a canonical complexity that you can use called sutured Floer homology due to UHAs that always decreases under a non-product suture manifold decomposition. Under product decompositions, it stays the rank of the suture Floer homology stays the same. And so anyway, so you pass to the sequence of covers, and the guts eventually simplifies until it's empty. When this cohomology, this suture Floer homology, for example, is trivial, and then you've found a covering where it fibers. So it's a sort of, there's a obstruction that the Riefers conditions allows us to pass to a cover to make the obstruction vanish. So that's sort of a summary of proof of this. Okay, so that's some three-manifold topology. So the next hour, then I'll talk about the virtually special cube complex result. Is there any questions on this? Okay.
So maybe let's take a 5-minute break and I'll resume. So we'll resume in 5 minutes.
All right, sounds good. Thanks.